And I'd like to move on now to our next talk, which will be given by Don Burgess. He is currently a research fellow at SIMS, but he's had another career too. He is retired as chief of the Warning Research and Development Division at NSSL. He has also served as acting director and chief of operations at the NEXRAD Radar Operations Center and chief of the National Weather Service Radar Training. He received his master's from the University of Oklahoma. He's also a fellow of the American Meteorological Society. He has over 50 publications and over 200 conference papers, and he has also served as an adjunct professor of meteorology at the OU School of Meteorology. So let's welcome Don for his presentation on forecast and warning improvements.
Thank you, Greg. Well, I wanted to start by mentioning, as others have, that I'm going to be talking about partnerships between SIMS and NSSL and the ROC in a lot of what I'm saying here. And these partnerships are so strong that the work is integrated. And so I'm not going to separate things out. SIMS is a strong partner in all the things that I'm going to be talking about. Also, I'm going to be slightly different than some of my colleagues. They have mentioned some of the individual participants, and I wish that I could do that, but I just don't think I'm able because there are so many important participants that I've just kept this more general. If you're out there and you've done some of the work, I hope you can take comfort in seeing some of your results presented up here. Back when SIMS was young, 1980-ish, we were still learning about some of the basics. We were learning about experimental Doppler radar signatures. We were learning about how they tied to storm structures. We had very little understanding of radar meteorology out in the field among forecasters. We had some projects like Project Doplight that took Doppler radar and lightning to Weather Service offices. SIMS people participated in that. We also had Scientific Storm Intercept that went out to verify the radar signatures and the understanding of the storm structures. And SIMS participants there made contributions. We also were trying to get a better understanding of mesoscale meteorology and near storm environments for these kinds of storms. I know the next talk will talk about some field programs, but I stuck something in from Project Sesame in 1979 with a surface mesoscale map near the time of the tornado outbreak on April 10th of 1979, Wichita Falls tornado. Going forward, we started thinking about the initial deployment of the WSRAD, the NEXRAD program, and thinking about detection of severe storms and displays and algorithms. And so some of the focus of the work in this partnership became the first type of displays and algorithms that went into NEXRAD. And you can see at the bottom, I have listed some of the algorithms that were initial algorithms that came from the work here. The SKID algorithm, hail algorithm, the velocity wind profile, VAD, mesocyclone algorithm, tornadic vortex signature algorithm, and a de-aliasing algorithm. So all these things contributed to the initial NEXRAD deployment. I can show you some examples here in the upper left for an outbreak in 26th of April, 1991, the Andover, Kansas, Red Rock, Oklahoma tornadoes. This outbreak occurred while the Twin Lakes radar was experimental, had not been accepted by the government, and it was some of these days like this that allowed that acceptance to occur and deployment to begin. So here you see the reflectivity field, and you see the storm tracking or SKIT output. Seems kind of elementary to us, but it was somewhat revolutionary in those days. This is velocity depiction with a mesocyclone signature and some information about that. And then on the right is the VWP, the wind profile, This was in clear air in central Oklahoma, and you can see the development of the vertical wind shear that was contributing to this tornado outbreak. So very good initial work, SIMS and partners contributing to the first deployment of the WSR-88D. But also improvements to the WSR-88D over time. I'm going to be talking here about single radar algorithms, and there's a whole litany of them. You can see mesocyclone detection algorithm. It goes on down tornado detection, hail detection, near storm environment, gust front, microbursts, improved velocity de-aliasing, multi-PRF de-aliasing algorithm, and rapid update of algorithms all came from this partnership that I'm talking about. And there were some algorithms that didn't get deployed in the 88D for various reasons. The damaging downburst and prediction algorithm and also the bounded weak echo region algorithm are in that category. Then we have dual polarization algorithms, the hail size detection algorithm of which some of you are aware. This is an example in the upper right. You can see the large and giant hail categories that come from dual pole information. Also, we have the tornado debris signature algorithm from dual pole information. That's still experimental, but we hope it will be made operational in the future. An example of it's on the right. Here you can see a tornado debris signature example. It is shaded, which is confidence, is that shading. The bright white is the highest confidence, and as it degrades down to blue, that's lesser confidence. Then finally at the bottom, some experimental algorithms that are being developed right now, a new mesocyclone detection algorithm, a new tornado detection algorithm, and a new hail detection algorithm. And there are some posters that will be presented later this afternoon on those experimental algorithms, and I think it would be a benefit for you to check with those folks about further information. In addition to just algorithms, a lot of work was done with displaying the data. Forecasters want to look at the data, they want to see the signatures for themselves. They do rely on algorithms, but more as the second line of defense. The first line of defense is looking at the data. And when we began back with the early deployment, we had displays that didn't display the full resolution of the WSR-88D data. The so-called level 2 data or full resolution was not available, and that only came as a function of time. The first displays done by NSSL, a system called WADADS, and those were put at Weather Service forecast offices to start seeing that data and seeing how it might benefit them. Also had algorithm data. Became the warning decision support system. There's an example here in the lower left at the time of the May 3rd tornado outbreak in Oklahoma, and you can see here the track of the mesocyclone from the Moore supercell as it's headed toward the town of Moore. Then those have increased over the years. SCAN, the System for Convective Analysis and Nowcasting, and then in AWIPS, the Four-Dimensional Storm Scale Investigator, or FSI, and here is an example of that display. Many ways to slice and dice the data at its highest resolution to get the most information out of it. Also, you may not be aware that when NextRad came along and the 88D radars were deployed, they did not have a good concept for archiving this base data, the level 2 data. And it was through the work of SIMS and OU and partners and NCDC that we actually have the archive system that we have today, starting with an experiment called CRAFT, Collaborative Data Acquisition Field Test. We began to use the growing backbones of the internet to start moving some of the data into Norman first, and then later to NCDC. And we even had, for several years, a center here in Norman with SIMS as a participant called the Integrated Radar Data Services Program. And you can see here in the lower right, in 2001, in Norman, we were receiving and archiving the data from 57 radars. So this internet archiving system didn't come immediately. It came in pieces, and we had an archive here in Norman from 2001 to 2004, at which time we then transferred it to NCDC, or now NCEI. Those improvements that I've talked about contributed to National Weather Service skill scores for warnings becoming better. I would call your attention here to a diagram of probability of detection on the left, or on the vertical axis, and year on the horizontal axis, and the thick red line. And you can see that the probability of detection was not very good before NextRad implementation. It improved by about 40 points during the time of that implementation, and we went from about 30% probability of detection to about 70% probability of detection. So a significant improvement, and that led to a Department of Commerce gold medal that Pam has already mentioned. And SIMS was certainly a participant in that medal. Now I want to transition, see how I'm doing here on time, still alive. Transition to going from single radar to multiple radar. Those systems that are multiple radar and multiple sensor in their applications have a significant advantage over any single radar system for very obvious reasons. And so that research has been going on at SIMS and Partners for quite a long time now. System was first called QPE SUMS, but then before too long was changed to MRMS for multi-radar or multi-sensor. And for severe storms applications, which is kind of my theme at the moment here in this talk, the applications are rotation tracks or shear swaths, and then the maximum expected size of hail or mesh in its swaths. And at one time, NSSL had an experimental on-demand system for sending out this information to interested users, and that very much involved SIMS. Here in the lower left is an example of rotation tracks. This is for the rather historic tornado outbreak that occurred on April 27th of 2011. Many supercells down here in the southeast, and you can see the individual tracks of those supercells, and even as it extended over into the mid-Atlantic states. These data are very useful for deploying resources for rapid search and recovery and getting aid to victims, and they're also useful for damage surveys, knowing where to look for the tracks of tornadoes. Here on the right side is an example of mesh, maximum expected size of hail, and you can see in colors here the depiction of large and giant hail. I think this is up in South Dakota, storm moving from northwest to southeast, but you can see the long extent of the track. You can also see overlaid reports of hail that came from a special program that was done here in Norman, SIMS and Partners, Severe Hazards Analysis and Verification Experiment, or SHAVE. And it was a very important contributor to getting the data to say what is a good algorithm to identify hail, because if you look at National Weather Service reports, which are marked on here, there are so few reports that you can't do verification with that data. Now I want to switch for a bit and talk about advances in quantitative precipitation estimation, QPE. And I want to thank Jen Zhang for sharing with me her slide that kind of has a nice depiction of all that and a timeline, and talking about single radar applications at the top for QPE, and then multi-radar or multi-sensor applications at the bottom. And with single radar, we had an initial system in the WSR-88D, which was reflectivity-based, PPS. And then in later years, we've had single Doppler systems that have involved dual pole data. And there's been an improvement because of that. But you can see here with the long development, including craft and being able to get the level 2 data, how we've been developing multi-radar, multi-sensor systems, And in 2014, then we had a full multi-radar, multi-sensor, and dual pole system for estimating precipitation. Whoopsie daisy. So I got ahead of myself. I was right here. And then we're just on the verge of even a newer and it looks like better system using attenuation with dual pole information, and the skill scores here are even better than the preceding systems. And I have been failing to mention, but for a number of these slides there have been posters that are going to be presented this afternoon. So please excuse the fact I haven't mentioned all of them, but hopefully you've looked at them as we've gone along. Also, this work then led to a Department of Commerce silver medal in 2015 with SIMS as a partner. Was that the yellow one or the red one? All right. I only have a couple more. I don't think I'm getting my full 20 minutes if that was the red one, but I'll go with that. Because I'm keeping track of time myself. With these MRMS QPE systems, we've done some really interesting, innovative things. We have a flash application. I don't have time to tell you a lot about it, but you can see when there's a threat here in North Texas, we can compare the rainfall estimate to the flash flood guidance. We can also look at the estimated stream flow, and that allows for better flash flood warnings. And we can also look at river systems. We can even look at storm surges with hurricanes as an example in the Coastal and Inland Flooding Observation and Warning Program, CI flow. So there are a lot of these applications in QPE where we're doing very innovative things and now being transferred to the National Weather Service. One thing I do want to explain, even if I'm about out of time, is that these forecast and warning improvements will not occur without training. We can develop all kinds of good things, but if we don't train the forecasters in the use of that information, then they're not going to succeed. So we have a long history of that collaboration with SIMS, and that's both in the severe storms area and in the QPE flash flood area. And a number of names of this organization, Operational Training Branch and FIRST and Warning Decision Training Branch and now Warning Decision Training Division. And they've done things like tornado warning guidance that was very helpful to the field, distance learning courses, workshops, and weather event simulator. SIMS people making big contributions, some of them standing up here heading workshops, first at a separate building in the past and now here in the National Weather Center building. This is a front of the weather event simulator. It is a very important device because it allows delayed real-time playback of data and allows forecasters to go ahead and practice their skill and be scored on important events. And all the data necessary, radar and other sensors, has been captured in the WES. Ask about forecasts and warnings of the future. The program here is FACETS, forecasting a continuum of environmental threats. You can see it has a radar grid-based and probabilistic background. It contains a number of other elements that I'm not going to go into, and it has the forecaster funnel concept from days and large time increments down to just minutes in very small areas. And I will stop with what the future might look like if we're using FACETS and we have an April 27th tornado outbreak. You can see in the dark blue is the smaller amounts of threat, and as we go to the brighter colors all the way to the white, which is extreme threat. So this is how a FACETS system might handle a tornado outbreak in the future. And with that, I'll stop and say thank you.
Okay, thank you very much. We'll have time for one or two questions, so you don't leave yet. Does anybody have a question or two? Okay, we'll ask one very quick question then. So you've talked a lot about our activities such as FACETS, MRMS, and of course the conventional radar. Do you see anything really new that will revolutionize what we do? Like, 40 years ago, I'm sure you couldn't foresee MRMS or FACETS or anything Do you have any idea what might be new coming on?
Well, I didn't mention it. But with facets, we have a continuum of threats. And what I see is the merging of programs like Warn on Forecast and these experimental kind of products that I've been talking about, and what the radar can sense, and how we can put that together, put that with Storm Prediction Center information, with storm scale models, and how we then would have a continuous flow of information and be able to handle the threat as it evolves.